All right. This page right here is really important for what we do after this, okay? So here we're looking at the rectangular and polar form, and we're going to look at representing complex numbers in both the rectangular and polar form and representing vectors that way, okay? So points, complex numbers, vectors. All right, so you want to think back to how you could have a point, and I'm going to use A and B here because A and B is used when we get to complex numbers. That's in a rectangular form, like an XY type form, or you can have it in the polar form, the R theta form, okay? So for instance, if we had the point -1 square root of 3, we've looked at this before, okay? Be like right there, not quite at 2. I need to drop that just a tad. Like right there, say, it's like at 1.7. There's the terminal side. This is the theta, okay? Then you drop that perpendicular, and that allows you to put these values on there. You know this is the -1, this is the square root of 3. So to get the polar form, you need the r and you need the theta. And so you're going to do the r by taking the -1 squared plus the square root of 3 squared would equal your r squared. So that's 1 plus 3. So r squared is 4, which means r is positive or negative 2. I'm just going to say positive because we're always going to do the easier version. Okay, so this is 2. Okay, so that goes there. To do the angle, we're going to use the fact that the tangent of that angle would wind up being opposite over adjacent, and make sure you put the negative on that so that you get the angle that's in that second quadrant. Okay, so that's going to be negative square root of 3. And so the angle would be the inverse tangent of that. Okay, but basically I'm just going to look at my unit circle and see that negative square root of 3 would be what I would get if I were at this angle in the second quadrant is at 2 pi over 3. Okay, so you just look at your unit circle and you see how at 2 pi over 3, the ordered pair would be -1/2 and then square root of 3 over 2. So if you did sine divided by cosine, that's where you would get that negative square root of 3 right there. So we know that has to equal 2 pi over 3. And so there you have it. Okay, so there's the rectangular form of a point, and here is the polar form. Well, when we go and we look at complex numbers and vectors, we can write a complex number in its standard form, and it's any number that can be put in the form a plus bi. But a lot of times when we're thinking about that, we kind of think about it as an ordered pair AB, a little bit different than what you see there, because what I'm going to do is have this x-axis be the real set of real numbers and the y-axis be the set of imaginary numbers. And then when I take something like -1 plus square root of 3i, the a is the real part. The b is the imaginary part. And I can think of that complex number, -1 plus square root of 3i, I can think about it as the ordered pair -1 square root of 3 and plot it like I would a point. So this is the real part, this is the imaginary part. So I go to the left one on the real number axis, and then I go up square root of 3 on the imaginary axis. So that's the connection between the complex number and the point in the rectangular coordinate system, okay? But we're going to be doing some things later where it's to your advantage to have the complex number written in polar form rather than as in rectangular form. So this is the rectangular form of a complex number right here. Okay, but when I see it, I kind of think of it as the ordered pair, -1 square root of 3. Right, with the complex number in polar form, you just need to know what it looks like and then it'll make more sense. So it's going to look like this. It'll be r cosine theta plus I sine theta. So you need to determine what the angle is and what the r is. And you basically do what you saw right up here, but you're just thinking about this being the real number axis and this being the imaginary axis when you're thinking about it. So you know how we already found that r was 2? So r is going to be 2. And then you know your theta was 2 pi over 3, so you just plug that in. And right there is your complex number written in polar form. Okay? And the reason that works is because you know how r cosine, if you distributed that r, how that would be r cosine theta plus I r sine theta. And that's really your x, and that's really your y. That's really your horizontal component, and that's your vertical component. Okay? All right, now some of the terminology I want you to know. The r that we had, that's called the modulus, and you represent it with absolute value symbol. It's like the length. It's like the length of this right here. Okay? It's the length of that. So you can't really talk about one complex number being greater than or less than another one in the usual sense, but you can look at the magnitude of it or the length of this right here. Okay? And so it turns out to be equal to, r is just the square root of, typically we say x squared plus y squared, but I'm just using a's and b's. Okay, so we would find r by doing the square root of the a squared plus the b squared. That's called the modulus. So I don't care that much about vocab, but you'll see it sometimes on the problems and you'll wonder what it is. Okay, and then the angle you can find by just doing the tan inverse of b over a, that's like y over x. And then the angle is called the argument, and this kind of harkens back to functions, discussion of functions. Theta is actually the input to the function, or the what you might call the argument. So you might see that language. Okay. And we're going to use this in a little bit. I just want you to kind of see an example and have one page that shows the relationship between those things. Okay. All right. So now let me see if it'll let me move without moving stuff. Yep. All right. Now let's look at vectors. So vectors are closely related to what we had earlier. The difference is going to be that when I think about that point, I'm going to use that same example. When I think about that -1 square root of 3, and I plot that point, the vector is going to have a direction to it. So it's going to be an arrow from the starting point to where you're trying to get. Okay, let me erase that. I don't want that point. What are you erasing? So let me just draw that again. I don't want that point at the origin. That's why I erase that. Okay, so with the vector, I still want to think about that same point, -1 square root of 3, but I'm just going to have that vector that ends at that -1 square root of 3 spot. Okay. All right, so when a vector is written in rectangular form, it looks like this. Now, in books, they'll just use a V, but it will be bolded. Since I can't really do that, you'll see that little symbol a lot of times written over the top of it. So it's going to be A, I, not the imaginary I, just a nice straight up and down I, plus B, J. Some number I plus some number J. So this particular vector over here, that vector is equal to -1I. You could write it -I, but I'm going to emphasize the -1I plus square root of 3J. Okay. And then A is called the horizontal component of the vector. And B is the vertical component. Later, these will have to do with forces. You'll draw these pictures. You'll use vectors to represent the forces when you're constructing things. Okay, now let's look at the polar form of a vector. And see how basically it's just that point, -1 square root of 3. It's just written in a different form. So I kind of want you to see that, that this is the vector. This is the complex number. Okay. And then here is the point. And they're all very closely related, aren't they? Okay. All right. All right. So now we're looking at vectors written in polar form. So we're still talking about the vector. And here's what it's going to look like. A lot like the complex number earlier. It'll be r cosine theta with the I, and then r sine theta with the j. So basically just replacing the horizontal piece with r cosine theta, because that's basically your x, and the vertical component, replace it with r sine theta, because that's basically your y. Okay. And then if you hadn't already calculated your r and your theta, you would do it just like we did in the very, very beginning for a regular point. So we found out that r was 2 and that theta was 2 pi over 3. So you're just going to plug those in. And that's your vector. So it's a lot like the complex number. Okay. Now, special vocabulary. The r, when we're talking about a vector, is called the magnitude. That's why sometimes I say magnitude, because they're basically the same thing. I say magnitude a lot of times when I'm looking at this, because basically that's what it is. The absolute value of your complex number is really the length of this right here. And that's exactly what the magnitude of the vector is. So r is the magnitude of the vector. But it turns out to be the same as what it's been on all the rest of them. Square root of a squared plus b squared. Okay? So it's pretty much the same as what the modulus is, and it's the same as what r was in the beginning. I'm scared to move it. I don't want it to move. There we go. Okay, so you know how here your r turned out to be right there. You can see it. Your r was found by taking a squared plus b squared and then just square rooting it. So it's all really the same thing, even up here. Okay. All right. Now, the angle that we find by doing the inverse tangent of the y over x, which is b over a, that's the direction angle. Okay, so you determine the direction angle, and then you determine the length of the vector, and that tells you how to draw your vector. Okay. All right, so I'm going to stop at that point. You want to take good notes on that, and then have that sheet almost as a reference as you're doing some of the problems in the homework. And then I thought I'd go in and work some of the problems dealing with complex numbers. Okay. All right, I'm going to do that in a separate video.